everything else, there's a set of criteria that you follow. All right. And rubric. The assessment designed to allow students to apply mathematics pedagogy that we've been covering in class. The same blurb that I used in the last one. You're expected to participate and so on and so on. All right. So the assignment. First, you start off by reading the article and then choose one of the topics from the next gen topics list that you're familiar with that we used for the first assessment. That was the designing an activity. Right. Indicate the grade level and the domain, whether it's geometry, measurement, data, and so on. A brief statement explaining why each question was selected. That's something that you would never have on an actual, like if I were giving you a test, I would never put next to each question what my rationale was in selecting those questions to be on the test. Although it kind of makes sense to do that. It's just, it would be distracting from the question and also it'd be a pain. But for this, I want to get an idea of why you chose those questions. A rubric and or an answer key for the assessment. If it's a traditional test, then an answer key with an indication of what would lose credit, what would gain credit, that would be important. Outcomes for the students, what happens if the student performs, students perform well or poorly. Right? So those are things that you want to keep in mind. Now, historically, people have kind of interpreted that little bit as they performed well, so I'm going to give them a sticker. They performed poorly, I'm going to hold them back in during recess. That's not really what I'm looking for. What I'm looking for is how you're going to diagnose from the assessment where their struggles are and what you're going to do in order to help them overcome those struggles. All right, and then you can see the rubric that you'll be graded on, which is a simple rubric. It's very similar to the one from last time. Right? In fact, it's almost with very, very minor edits, a straight up copy paste job from the last one. Right? So the expectations are pretty, I was going to say clear, but I would say more so consistent. Right? So in terms of what you're asked to submit as a product, it's definitely not as intense as the last unit. With there's no video requirement or anything like that, but but I am looking for something substantial. All right, so figured I'd take a few minutes and talk about that. We didn't have class last week, and I know some folks would either do one of two things: completely forget that this is a thing, possibility, or and I know some people already turned it in, so it's fine. The other possibility is that you just kind of go down the wrong path. And I wanted to make sure that I at least talked about it a little bit so that you didn't run into that. Okay. So that's that. And that'll put a ribbon on unit 2. So let's talk about unit 3, the final unit in the course. You'll see, actually, let me go back for a second. You see the date range was 11/3 to 12/1. 11/3 as in like the class we didn't meet, but that's kind of not really relevant. The 12/1 part is the part that I like to speak on. The unit itself will end in the beginning of December. And then after that, we get a couple of weeks, one where we'll do an assessment and then another where we have a final exam, right? So, well, final course assessment. So a little bit different because as you've become familiar with, hopefully throughout this course, it's really not as much about the tests as it is everything else. Those skills assessments, they always seem like they're really heavy weighted and so on, but they're just another assessment, and they're hopefully you've been finding them to be fairly straightforward. There's some pitfalls here and there related to the pedagogical stuff, but not in terms of actual mathematics. So that's something that you should be looking forward to rather than trying. Anyway, clicking on unit 3. We got all this stuff here. Again, I have these as placeholders, so ignore them, the investigations. And kind of moved away from that because I don't really like them. I never really did. And especially in the remote environment, I tried them for the first unit, and it was so choppy, So I figured, I'll keep them in, but I'm not going to really do much with those moving forward. So topics of study, we're talking about multiplication. You have some reading opportunities if you want. There will be a small technology assignment in this unit. I'm actually in the process of revising it, so don't feel like you missed anything yet, because I haven't posted anything meaningful related to the technology assignment for this unit. Right. Course resources we'll get to in a minute. There's also a course evaluation. They ask us every semester to select a class to have an evaluation for. So this is where you go. If you remember these things, it's a survey about your teacher, and how terrible they are, So that's what I'm asking you to do. But I like to give you a little reward for it, because I know it's not really a pain. I wouldn't say it's a pain. It's just something extra, and I'm not a big fan of asking people to do something extra without compensating them for it. So tomorrow you'll have a survey link in your email. If not, then you can go to any of these other places to get that survey link. So it's not ready yet. It's gonna take place tomorrow. So this shouldn't even appear on your Blackboard, but it appeared on mine. So I figured I would talk about it. Tomorrow it'll appear, and you'll have the opportunity to kind of turn the tables on me and just go down the list of all the things that I'm terrible at. Organized, nah. This guy doesn't have anything in order. Always late for class, like whatever, whatever you want to say. Honestly, I selected this class for a reason, and that reason had everything to do with the fact that I've taught it before, but it's not like I teach this class every single year, and I'm always trying to improve it. And especially with the remote environment, my goal is to try to make this a class that could be either in person or online, or a hybrid course. So the feedback is actually pretty useful for me. I can't say that about every class, because when you teach a class long enough, it's like, what kind of feedback are you going to give me? I mean, I've been doing this for 20 years, but this is the class where I could actually use it. So yeah, please take that seriously. Give me some honest, but nice, like don't be mean about it. I do have feelings, but also, feel free to give some constructive criticism. And, I don't see the results of this survey until the middle of next semester. So you can be honest, but when I do see it, I do think back and be like, whoa, that was harsh, or, oh, that was nice. But what I will ask you to do before this semester is over is I'll ask you to complete a survey for me. All right. So this is for the college. I get the results for it, but I'll ask you to pretty much do kind of along the same lines, complete a survey, just giving me some feedback on the way the course was constructed, and the goods and the bads and all that stuff. All right. So yeah, more on that later. And like I said, I don't ask people to do anything extra without compensating them for it. So there will be a small quiz grade associated with that. All right. Just understand, very, very important, because people have not been happy about this. This isn't bonus. Right? This is a quiz grade. Now it's basically a free quiz grade, because you can't screw it up unless you don't do it. So if you complete the survey, when you complete the survey, I'm going to be glass half full here. When you complete the survey, which again will be available tomorrow, you'll get a little receipt. Take a screenshot of that receipt. Submit that on Blackboard. All it'll say, and you'll see, all it'll say is your name and that you completed a survey for me. And just for doing that, I give you 5 points, 5 quiz points, 5 out of 5. right? So like I said, it's not something you can easily screw up. I'll make some reminders as we go forward, but I've reminded people in the past semesters. I would remind them like daily, and there's still people that miss the deadline and come looking to make it up. There's no making this up. You won't have access to it after the deadline, which is December 1st, right? So so once it becomes available, just do it right away and you'll be fine. All right. That's that. So just getting the housekeeping stuff out of the way. Now, as far as the notes are concerned, course resources, wait half an hour for it to load up, of course, because why not? Blank notes. Oh, apparently trash has changed. Cool. They really don't want to catch any flack for that because I get that every single time I log in. All right, we're in lesson 4.1 to 4.5. All right, so click on that, open that bad boy up, and you'll get the completed notes on my website through the course resources after every class. So, so this is where we're going to start, and yeah, talking about multiplication. We're finally there. Let me stop this share. Let me pause. Resume recording. Oh, something in the chat. Oh, so the question was how many questions should be on the assessment? I didn't want to force that issue, and so that's a really good question. But I didn't want to give a specific number because I know some assessments don't require more than five or so questions, and some of them, if you really want to hit that topic the right way, you might need like 50 questions. So the short answer is it depends on the topic that you choose. What I will say is if you're not sure, if you think that you maybe have hit on every single way that you can attack a concept, because that's the whole thing. Just remember, we have the three modes of mathematical instruction. You got the visual, right? You got the verbal, and then you got the numerical. Right. So you want to, for every topic that you're including in your assessment, you want to make sure you get that from the students. There's some questions where you can just put it all together and say, a word problem, whatever. Mary's doing this, John's doing that. Give me the answer and justify it with words and a diagram. So they have to do all three things. So, yeah, I mean, it is possible that you can get the job done with 2 questions on an assessment. But then if you want to chunk it smaller so that they're not, doing a whole ton of work for 1 question, then you can break it up, in which case you need more questions. All right. So if you hit on those 3 modes of mathematical instruction, you're probably pretty good, pretty okay. What I will say is if you're in doubt, send it over to me. I'll take a look at it and I'll give you some feedback, and then you can revise as needed, or you can just message me and say, "This is the topic that I chose. I'm thinking about 5 questions, and these are the questions that I have in mind, or these are the types of questions I have in mind. What do you think?" And I'll be honest with you. These assessments are more like a collaborative thing. They're not designed for we already did the test. So they're more so that you can develop a useful product, and we even learn through failing, and not failing, grade wise, but failing to achieve our objective. Sometimes I give a test, and what I learned by giving that test is that I didn't do a good job of teaching whatever concept was related to number 3. My first instinct, because I have a lot of pride, is, well, obviously they didn't study the content. That's why everybody got number 3 wrong. And I sleep on it and I think about it and relax a little bit. And then I realize, yeah, probably could have done a better job of explaining that one. So even if you don't have the best questions, you might think that they're the best, but then when you go to deliver this assessment to somebody, like you got a teaching job down the lines, and you give this assessment, and half the class gets a question wrong, that's when you kind of go back and look at it again, right? So it doesn't have to be perfect. It just has to have perfect intentions, all right? So yeah, long story short, send it over to me. If you send it over to me before the deadline, I'll take a look at it. I mean, maybe not with a fine tooth comb. I'm being honest here. There's a ton of things to do, but I can spare some time to give it a quick once over and let you know my thoughts on it. All right, and that applies to everyone. All right. So we're going to talk about multiplication, and it's kind of weird to think about the fact that we're going to spend like a month talking about multiplication, less than a month. To be realistic, right? Because it's a multifaceted concept. There's a lot of stuff going on in multiplication, and there's a lot of ways to think about it. And in fact, I even got to a point where I made it to my adult life. And there have been situations where I got like 5-10 years into my teaching career, and I still didn't know why we multiplied for a particular circumstance. You know, and so it isn't until you really sit down and explore it that you kind of get to the bottom of that. But it kind of comes down to the idea, you know, students are always going to balance the need to get stuff right on a test. All right, well, what do I do? I just multiply? All right, fine. Stop talking. I don't need anything else. Just tell me what I got to do. I got to multiply. All right, cool. But now you don't understand why you're multiplying, right? But there's only so many hours in the day, so they sacrifice the understanding for getting stuff right. But then down the line, it's like, well, I probably could benefit from knowing that. And then you end up in that kind of conundrum where it's like, I really want to know it, but now I'm an adult and I don't have time to sit down and think about this crap. And I'll tell you, there's some people, and I've seen it firsthand, I've experienced it firsthand, that don't start to understand certain mathematical concepts until they're showing their kids how to do it. You know, like, so this is what we're doing. That's why that works the way it does. Yeah, that's part of the fun, you know, but it's a lifelong learning experience, right? So multiplication is not really a basic operation. So look, you know, what does that mean? Well, what it means is that multiplication is really just kind of a shortcut to the real basic operation, which is addition. Right? In its most basic sense, that's what multiplication is, or what it started out as. We're looking at being able to get results of addition much more efficiently. Right? So a little blurb here. It is possible to solve many multiplication problems by using a simpler operation. And I can say that elementary education starts off now with really kind of like targeting and zeroing in on the concept of addition to the point where it's like, shouldn't we have moved on already? Shouldn't we have moved on to multiplication? Why are we still adding? First, second grade, even half of third grade, it's still addition. And then all of a sudden it's multiplication. And, you know, if it's performed correctly, the students don't even realize that they already have an intuitive understanding of multiplication. Okay? And so that's the plan anyway. So you have this exploration here. Solve the following problems using addition and appropriate units. Draw pictures if it's helpful to do so. You know, like if it's your students, then you would state directly you want them to draw pictures or not. Right here, it's like, well, you know, you draw them if you need them. All right. So 3 children are playing a game. Each child gets 4 cards. How many cards are in use? All right. So, you know, like you kind of look at it and say, well, I know the answer, but you also got to look at it and say, well, you're explaining this to a first grader. And that we keep coming back to that. Right. So 3 children play a game. Each one gets 4 cards. So I'm going to draw 4 cards. That's not a card. Rectangles. It used to be so easy on this app. Ooh, it's more of a parallelogram, but I'm going to live with it. I'm gonna like do a little overlap to show them in sets. All right, so I got my 4 cards for each kid. All right, so we can label it up. We can say child 1, child 2, whatever. You can just believe me, I guess. I'm going to chuck it in here, child 1. All right, so that we get a nice visual here. It's pretty easy to just kind of go through and say, well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in total. But it really just ends up being a matter of saying, well, first off, we want to be like, how do we get that? What we did was we took the 4 the child 1 had, the 4 the child 2 had, and the 4 the child 3 had. All right, now this is repetitive addition, giving us 3 of those 4s, which it amounts to a 12. All right, so what we're looking at, and we'll generalize this later, but this is, we'll just kind of keep it in mind that we have 3 4s. All right, that's the key ingredient there. That verbal understanding of what's going on here. 3 4s. All right, and that leads us to the concept of multiplication, but I don't want to rush the process because we're talking to little ones, you know. We don't want to just tell them, okay, well, that means 3 times 4, which is 12. We're like, whoa, 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 I was with you until you brought out that 3 times business. What was that all about? You know? So the idea is to slowly build your way up to it. A rectangular quilt is made of 4 strips, each containing 6 squares. All right, so how many squares are in this quilt? So 4 strips containing 6 squares. So I'm going to draw a strip. And I'm going to have it contain 6 squares. Yeah, eventually I will. All right, so that would be the 1 strip. I'm going to shrink it down because I want to not be short on room here. So there's 1, 2, 3, and 4. All right, so each one of them has 6. So again, it's the same deal. So I'm looking at 6, 6, 6, and 6. And we're adding them up. And that gives a result of 24. But again, it's what we get from this. It's not so much that, okay, I can add 6 plus 6 plus 6 plus 6, but it's really more so that we're looking at 4 6s. And, you know, like as you go forward, you say, well, maybe I don't need a diagram, but I would actually encourage you to kind of sort of fight that urge and say, well, let's keep with the diagram because then you have that visual component going on, you know, and then when you're explaining it to students, having those diagrams there, they make a big difference. Rachel has 2 pairs of shorts and 3 t-shirts. Assuming color coordination is not a factor, How many outfits does she have? All right, so 2 pairs of shorts and 3 t-shirts. Now we're kind of moving away from this, similar ideas here. They're not all getting the 6 squares. They're not all getting 4 cards. In fact, Rachel is the one that's getting all of her things, but we're looking at 2. Right. We're looking at 2 pairs of shorts. Let me just make sure. All right, one second. I don't know who that is. So we could look at it and say, well, we got the short. I'm not going to try to draw shorts, so my my ability to draw is limited to just like whatever this app is going to draw for me. So I'm going to say shorts 1 and shorts 2. And then we have 3 t-shirts. So t-shirt number 1, t-shirt number 2, t-shirt number 3. And if we want to box those in, I guess that's fine. But in this case, we're talking about a little bit of a different different take on this concept. Oh, why did I strike that out? All right, so that's the extent of my drawing ability. All right, so this is what we're working with. And we could look at it in a couple of different ways, but it really just ends up being sort of a counting approach to things. So I'd have to say, in terms of the outfits, we could be looking at the first pair of shorts with any of the t-shirts. So that means that the first pair of shorts could happen in 3 different, ooh, that's weird. 3 different possible combinations. Or really arrangements.
Professor.
Hmm.
Wait, the students would say something about the color? Are they like that?
What's that?
But the students say something about the color? You see how you put assuming color coordination is not a factor? Like they think like that? Like, oh, well, what color are the shirts?
Well, that's the thing. In most cases, I would say no.
Oh, okay.
And so I wouldn't necessarily explain that to them. It's more to explain it to you all. But there is, and I've experienced it before, where I'm teaching students and they're like, and I made the mistake of actually being very descriptive with the type of outfits that you can have. So I was like plaid shorts and a striped t-shirt or something like that. And then the student was like, those don't go together, right? And I'm like, it's just a math problem for crying out loud, But so I do end up having to kind of spell it out for them sometimes.
Okay.
Right, so our different possible arrangements. So it takes a little doing here, but honestly, I'm just making it take a little doing. I don't know. I don't know why I'm so fixated on making this look halfway decent. It's really just kind of a weird thing for me right now, but just the idea of just writing S's and T's, it just didn't feel right. So these are our possible groupings. So I'd be looking at 1. Oh, that just made it look ugly. 1, 2, 3, 4, 5, and 6. So then the big question would be, you know, and aside from me making this probably more complicated than it needed to be, there's got to be a quicker and easier way, of course. And really, if you just think about it, you come up with it. You come up with it pretty quickly and easily. You know, we're looking at 2 possible types of shorts and 3 possible types of t-shirts. But this goes back to what I was saying before. You know, I made it all the way through my adult life without really, not through my adult life. I don't want to be ridiculous about it. Into my adult life without knowing under what circumstances multiplication applies. This is one of those situations where it's like, okay, well, 2 times 3 is equal to 6. Yeah, there's 6 outcomes. Let me fix that. There's 6 outcomes, and 6 is the product of 2 and 3.
There's a question in the chat.
Oh, indeed. Well, yeah, I understand that. That's kind of a weird language thing. When they're saying 2 pairs of shorts, they're counting the short legs. You know, like a pair of shorts is one shorts. Right? So it's like each leg is a short. And then when you put them together, that makes a pair of shorts. It's really kind of strange. One of the quirks of the ways of speaking, you know. So like a pair of pants. That doesn't mean I'm talking about 2 actual set, you know, two jeans. You know, it's like each one of them. Like if I get up and I get dressed in the morning and I throw on my pants, I'm throwing on a pair of pants, right? Because each one of those pant legs is a pant, right? So that's a straight. And actually, that's like, you know, it's a great question, because when you get into problems like this, sometimes the individual might not have experience with the context. You know, when we're talking about a water bottle with a certain capacity, most people are going to have some experience with the idea that a container can hold a certain amount of something. But you know, if it's a matter of, you know, just changing a word choice to make it a little bit more easier to understand, then that's a good thing. Right? But we're looking at 6 as being the product of 2 and 3. Right. Now, the bigger question is, okay, how could we have understood that without having to draw all this stuff out, right? So that's where a verbal understanding kind of comes into play. So we have a computational, we have a visual. We definitely got a visual. I certainly took my time with that to a fault. But in a verbal sense, what we could say is, for each pair of shorts, we have 3 options for a t-shirt. So, and since there are 2 pairs of shorts, 2 times 3 would be equal to 6. All right. But I'm going to kind of play devil's advocate with myself here and say, and I'm stealing my own thunder by doing this. I'm the student in the class saying, okay, yeah, but how did you know to multiply? like here, okay, we got a 2 and a 3. How did I know to multiply them? Yeah, I know it gave me the picture, and there were 6 outcomes, but I'm not drawing a diagram every single time I got to figure this out. How can I understand and know when it's multiplication without having to do all that stuff? Right? And it really comes down to having a really solid, firm understanding of the concept. So we hit it from different perspectives. Like I said, we got the diagram, we got the computation, and now we have the verbal explanation. That didn't get it done. Maybe a tree diagram. This is where I'm stealing my own thunder because I do this again later on in the notes. But if you have one pair of shorts, you could have 3 possible outcomes, right? T-shirt 1, T-shirt 2, T-shirt 3. For my second pair of shorts, and this is really just a diagram talking about what I wrote here. For each pair of shorts, we have 3 options for T-shirts. Okay, so T1, T2, T3. All right, and so we're looking at a 2 by 3 situation. Okay, and so we have our 6 outcomes this way. 4 quality squiggly bracket. Right, so we're kind of hitting it from all different angles here, but that's how important this concept is. We're trying to do it in such a way that we're going to nail this concept home, you know, and it's not always easy for folks to understand. You know, again, you're still going to have that student be like, yeah, I see all these examples of it giving me the number 6, but how do I know, based on the wording of a problem, how do I know it's multiplication? And you know, some parts of it are going to be experience, and some parts of it are going to be more intuition, but it has to do with the fact that the experience has already happened. Right? So that's the point of these explorations, is to kind of try to guide the thinking. So I'm just making this a little bit bigger. A water bottle has a capacity of 1.5 liters of water. How many liters of water can 5 of these bottles hold? All right, so it's going back to the idea that we're taking that concept of addition and we're repeating it. Right, so 1.5, 5 times. Now, this would be addition. Relating it to something that the students would understand can be a powerful tool, where you'd say, okay, well, if I gave you 10 cookies and each one had 5 chocolate chips in it, how many chocolate chips do you have in total? You know, you could lay out those cookies, draw a picture with those cookies, and then just start counting up the little black dots in there. And then you'll see, this really is the same idea, except it's a little bit more abstract. 1.5 liters of water rather than saying chocolate chips within a cookie. But it's really getting at the same concept. All right, now this is going to be the same as 1.5, 5 times. I remember when I was first helping my son understand the concept of multiplication, very simple word choice. It kind of made the difference, because the problems were posed as, you know, something like 5 times 4. And I'm like, okay, 5 times 4, what is that? No idea. All right. All right, what about 4 times 5? Still no clue. All right, so going back to the 5 times 4, let's say, all right, listen, instead of 5 times 4, what about 5 4 times? Can you do that? Yeah, once he realized, oh, it's just taking 5, right, counting by 5s, 5, 10, 15, 20. Oh, it's 20, and that's it. That gave him the concept of multiplication. And really, that's all there is. That's all there is to it. That opening blurb that talked about multiplication not being a simple operation. It's because it's addition. Multiplication is addition, right? It's just a rapid form of addition. So when I say 1.5 5 times, or its equivalent 1.5 times 5, I'll use the dot for now. We'll talk more about notation in a little bit. 1.5 times 5, you're getting at the same idea, all right? And sometimes that little word choice makes all the difference, right? Now, it gets a little bit more complicated when you get into like fractions and percents and stuff like that. You know, if I'm saying like 10 times 0.2, I don't know how much it helps to say 10.2 times. You know, the student would have to have some pretty intuitive understanding of what 0.2 represents in order for that to be meaningful. But at least for whole numbers, it can be helpful, right? So then it's a matter of saying, all right, well, what does this give me? Now, I'll tell you more times than not, and this is anecdotal, this is personal experience. I find I'm going the other way, where if I'm given a problem like 1.5 times 5, I'm looking at that as, okay, that's 1.5 5 times. All right, so 1 5 times is 5. Now I need a half 5 times. All right, so 1 of those 1/2 is a half. 2 of them is 1. 1.5, 2, 2.5. Or add that to the 5 that I already had, and I get 7.5. Right, so I'm actually using, in more cases than not, I'm using addition to help me with the multiplication, which is kind of weird, because you would think that if multiplication is a shortcut to addition, you know, why would you do that? As leaders. But that's the idea behind it. You know, fluency going back and forth. You know, if you're learning a foreign language, you don't just learn to translate English to Spanish. You want to go the other way too. You know, you want to understand, if somebody's speaking to you in Spanish, how you can translate that back to English. Right? So that's part of the conversation, right? No different for math. It's just numerical instead of more verbal. Right? Now, just to give you a little bit of insight of what I was talking about, I was doing a lot of hand waving when I said it. This is what's going on in my mind. I'll show you real quickly. So I have all this stuff, right? So I strip it down. I pull out all the fractions. Put all this together. So that gives me a 5. I just kind of hold that in my mind. And I do the same thing with the halves, except it's not just a simple matter of counting by, you know, like counting by ones. You're counting by halves, but that's not really that bad, right? You wouldn't think so anyway. Count, you know, like I encourage the students to equate it to something that they're more familiar with. So half is 50 cents. Can you count by 50 cents? Yeah, 50 cents, $1, $1.50, $2, $2.50, 2.5. Right, so I got my 2.5. No, that's a little too thick. Put them together. and we get a result of 7, and that's not a 7, 7 and 1/2. But the goal is to get that to start happening in their heads rather than on paper, or by fingers and stuff like that. I remember back in the day, counting on your fingers used to be like an embarrassment. Like, oh, count on your fingers. What are you, some kind of loser? And they never said that. It wasn't that bad. But it was frowned upon. It was like, oh, we got to do this without counting on our fingers. I swear some of my best mathematical computation comes about using these little fingers, these little jammies. Right? And that's because I'm saying, all right, because it's an organizational strategy. I'm saying I'm taking 1.5 and adding it 5 times. All right. So I got my 5, right? So I'm going to hang on to those 5. And I go a half. All right. One of those halves, get up to a 1. Another half gets me to 1.5. Another half gets me to 2. Another half gets me to 2.5. That's how I keep track of it. Like it gets the job done. That's what we want, right? Now, I think what they were going for is if you're adding 18 and 7, the goal is to not have to do that with your fingers, right? To say, okay, 18, 19, 20, 21, 22, 23, 24, 25. Okay, I got it. That it's the simpler stuff, but using it as an organizational strategy, there's nothing wrong with that. Nothing wrong with using your fingers, right? Fingers, toes, whatever you got, right? So the second little part here, each of the problems in part A involved repeated. I can actually get rid of this. I don't even know why I have it. Involved repeated addition. And repeated addition is multiplication. So each of the problems in part A could have been solved more efficiently using what operation? Multiplication. Therefore, multiplication can be defined as repeated addition. All right. The following sets here, we got a couple of hearts in each one of those ellipses. There are blank sets of 3 sets with 2 hearts in each set. The union of these sets, mathematical term, you've never used this with your students, at least not until they're much older. But if you were to combine these sets, you would end up with 6 in total. No, you could say 6 hearts, but 6 in total is what I was looking for there. In other words, 3 times 2 hearts will give a total of 6 hearts. All right. In this problem, 3 represents the number of sets. And 2 represents or refers to the blank, actually a little typo there, number within each. Number within each set. All right. So number 4 in part A, 5 referred to the number of bottles. And 3/4 of a liter referred to, no, that's typo. Really 1/2 of a liter. 1.5 liters. Referred to the amount in each bottle. There's some typo bonus for somebody. Right. In these situations, it seems that one of the numbers in a multiplication refers to the amount in each object, and the other refers to the number of objects. Could say it the other way around too, because we know that multiplication, just like addition, is commutative. It's a commutative operation. In all the above problems, answers can be found by using repeated addition. So many situations involving repeated addition that this process is called multiplication. All right, repeated addition or multiple additions gives us multiplication. All right, so that was intended to be kind of an intro to the concepts of multiplication or concepts within multiplication. What we want to be able to do is start applying that information, but we're going to do that in a sort of a case-by-case basis. So the basic definition for M, a whole number, the product M times B is the total number of objects in M disjoint sets, each containing B elements. M is called the multiplier and B is called the multiplicand. All right. So kind of like radicand, if you're familiar with radicals, you know, it's the number that is being operated upon. All right. So in this case, we have the individual quantities, those would be the multiplicands, and the multipliers would be the number of objects in general. And that's really what this whole blurb is talking about, number of set sizes, set all that stuff. All right. So just a quick example, just kind of bring it all together. Melissa invited all her running friends over for a morning run followed by brunch. She bought 3 dozen eggs for the occasion. How many eggs did she buy? So again, this goes into the language associated with, well, mathematics, but also everyday language, right? Because if we do it with a diagram, you can go the route of a dozen eggs, but it does have the expectation that the students would know that a dozen is 12. All right? So they need to have that kind of background information. So all right, so that would be 1 carton of eggs, at least the best I could draw it. So in terms of a diagram, pretty easy. We would just count them all up. We're gonna have 36 eggs. But if we're looking for this, this relationship, the basic definition, so by definition, we'd be looking for the number of sets, in this case 3, and the number per set, which is 12, and then we would multiply to give a result of 36. Okay, so she'd have 36 eggs. All right, so in terms of computation, it's not bad, but it's always going to come back to that basic idea of, yeah, but how'd you know multiplication was the way to go? You know, make the connection between the repeated addition, multiple additions, multiplication, right? It really would be nice if somehow multiplication was the merging of those 2 words, multiple and addition. If you were to somehow conglomerate those 2 words together to create the new word multiplication, but it doesn't quite fit, but that's the idea. if you were to take, I'll try to do it visually, multiple in addition, and just kind of smush them together, right? You know, just kind of merge those two words. Like I said, not quite, but that's the idea. If you merge those two ideas or those two words together, you get this new relationship that is multiplication. That has all sorts of other applications to it, but that's really the origin story behind it. If you really think about it, it's like multiplication comes from a need. Everything in math and science comes from a need. Where you think about, okay, well, I got, I'm a farmer and I have a chicken coop and I got a ton of eggs. You know, I organize them by the dozen. I want to determine how many eggs I have. I can count them all up individually, or I can count up how many cartons of eggs I have, how many dozen eggs I have, and use the repeated addition, AKA, or the multiple additions giving us the multiplication. Or I could even go further and group, if I have large, very large quantities, I can group smaller sets into larger sets. If I say, all right, well, every group of 10 eggs is going to give me 120 eggs, then I would count off every 10 eggs, right? And if you think about it, a good relatable example, although it's a little bit dated now, would be wrapping coins. If you ever experienced the joy of that and didn't use the coin star machine or whatever it is now, you know, getting those little the paper roll up thingies from the bank and wrapping those coins. You know, you get, that was it, 50 pennies per little roll up thingy. You know, every one of those that you bring in, you didn't go to the bank and turn them in and say, all right, well, I'm not really sure how much I have, so let me break these bad boys open and count them all up again. You knew that each roll was a set of 50 pennies. So I have 10 rolls. All right, so I have 500 pennies. So what does that equate to? You start thinking about that. You know, you got your $5 right there. All right. But then, you know, your older brother comes walking in with a roll of quarters, and he's got like the $10 worth of quarters all in one shot, and you're like, well, I hate you. Yeah, like you got a wheelbarrow filled with pennies going in, and I'm only getting like $10 out of it, and he comes in with like 2 rolls of quarters, and he's already got double what I got. Oh, it can be interesting. You know, you can think of all sorts of applications of multiplication, but the whole idea comes down to convenience, right? So, and even in the form of estimation, you know, if you know, like if you're counting up, you know, it could be anything. It could be like those small erasers. It could be M&Ms. M&Ms are popular, Skittles, things like that, in terms of counting activities in classrooms. Maybe not these days, but you know, historically they've been. You break them up into groups, but you don't necessarily count the number within each group. You do it by handfuls, right? One handful. That's it. I can get 50 M&Ms in each double handful, right? So I just kind of scoop it up. Okay, that's 2 handfuls, 3 handfuls, 4 handfuls, 5 handfuls. So now I know I got 250 M&Ms roughly, right? Give or take, right? It's a good way to get into estimation, right? But it's also reinforcing the concept of multiplication, because they're not counting each individual one. They're using that multiple addition, right? The words of and times, key words when it comes to multiplication, right? But of is a tricky one because it could be a key word for other sorts of mathematical operations. So that one is based off context, but the one that's easier to kind of relate would be times. So notice that of is the word we often use describe the size of a set. For instance, we might say that a platoon includes 3 squads of 10 soldiers, right? So a carton of eggs contains 12 of those eggs. Each one has 12 of those eggs. The phrasing indicates the total number that can be found by repeated addition, also known as multiplication. Use of the word of can be a signal to multiply. But again, it could also mean something else, because if I were to say 3 of the 12 eggs are rotten, I'm not asking you to multiply there. Right? That's actually more like division or a ratio. Right? So it's a tricky one, because the wording in math, we want to have keywords. We want to have cases where we say, if I see this word, I do that. But sometimes the wording can be, it can be tricky. And so it's understanding the concepts or the context and being able to draw a conclusion from there. Very, very important, right? So basically the moral of the story there is don't fall in love with a keyword approach to things, right? Because if you do, there's a price to be paid, right? And that price will have everything to do with complete and total misunderstanding of the concept, right? Times, you really can't screw that one up, though, right? Times can be often translated as of, yeah, but 3 times 5 can be 3 sets of 5 or 3 5s. But if you see the word times in the problem, unless you're talking about a clock, it's going to mean multiplication. So there are some that you can rely on, but there's some that you got to be really careful about, right? Factors and multiples. We talked about this a little bit. Factors and multiples are pretty oftenly confused for one another on the younger levels. So it's a little iffy, but when you get into vocabulary, mathematical vocabulary, you want to be thinking early and often, right? You don't have to have the students use the vocabulary themselves right away, but you want to kind of develop a little bit of muscle memory with them and also yourselves, where you're using the words appropriately so that you're modeling the appropriate use of the words for them, right? So multiplier and multiplicand are also known as factors. And that's an important distinction, because I don't like saying multiplicand. I feel like I'm gonna choke every time I say it, multiplicand, So it's a weird word, but it is a meaningful word. But if I tell you that they're also factors, it might bring a little bit of extra kind of understanding to it. The multiplier is the one performing the operation on the multiplicand, but they're both in effect factors of some other number. Whole number product is called a multiple, but it's also called a product, right? So, the example there, we got 3 times 2 is really 2 3 times, right? Which gives you a 6. 3 is the multiplier, 2 is the multiplicand, and 6 is the product. 2 is the size of the set. 3 is the number of sets, another interpretation. 3 and 2 are factors of 6, while 6 is a multiple of 2 and 3, so, or 3 and 2. I'll just highlight factor. All right, so those words, they're related to the same operation, but they have a different meaning within the context of that operation. All right. When you're talking about whole numbers have a finite number of factors, but they have an infinite number of multiples. Right. So the example there, set of factors of 6, 1, 2, 3, 6, set of multiples of 6. It's weird to think about 0 as being a multiple of 6. But if you're multiplying it by a whole number, what this is the result of 0 times 6. This one is 1 times 6. 2 times 6. 3 times 6, and so on. So 0 is technically considered a multiple of 6. It's just not a useful multiple of 6. this is another thing that you'd never say to the students, but this is what some call the trivial case. Because 0 is kind of a solution to pretty much anything when it comes to multiples. 0 is a multiple of 0. 0 is a multiple of 1. It's a multiple of 2. It's a multiple of 20. It's a multiple of 3,000. So it doesn't bring anything to the party, right? So it's kind of like a technicality, so we don't really consider it to be meaningful, so we call it trivial, right? But the ones beyond that, even 6, you can kind of think of that as trivial. A number being a multiple of itself, of course it is. It's the ones that are greater than the number itself, those are the meaningful ones, right? So that would be 12, 18, and so on. But part of this, the part of the understanding of this material, and also, kind of, making your way through this course, hopefully you've come to realize that there's some things where it's for your understanding, and there's some things for your students' understanding. This is more for your understanding. All right. So the progression, an example, product of 2 and 3 is 2 3 times, or 2 3s, also known as 2 times 3 in a bunch of different ways. We could do that in general terms also. So this would be x times y which corresponds to x y's. Now that's a weird one. That's a weird thing to think about. All right. A better way, or maybe not a better way, I don't know. You'll be the judge of that. X y times. So you could have x y's. So the x representing the number of y's that you want to have. All right. Obviously, you're not doing this with a first grader, second grader, third grader. But it's good understanding to have, because that corresponds to x times y. So I'm making a kind of a script x, and then I'm making a little bit more of a rigid x to make a distinction between the x and the multiplication symbol. X times y. We could also use parentheses, x, y. We could also, so this is all different forms of notation that you can use for multiplication, which is really very aggravating for people. It's like, why not just one form of multiplication? I got an answer for you on that one, and I'll get to it in a second, but let me just finish this. So this is the same as x parentheses y, x asterisk y, and x dot y. All right, all of those mean the same thing. Now you can swap those for any numbers you want. 4 and 7, 4 times 7, 4 sevens, 4 by 7, in all those different ways. All right. Like I said before, math and science evolved from need, and even the notation. All right. So it comes from the idea that in certain circumstances, certain notations are more useful than others. And the idea that in this step, I'll show you, I'll highlight it, this step right here, I had to be very careful about how I drew my multiplication symbol so that I wouldn't confuse it with the x variable, right? So there was a kind of a movement away from using the x form of multiplication when it comes to algebraic representations of values or operations. So there's that. But then you look at the asterisk and you say, okay, what possible use could that be? That evolved from keyboards, right? And I'll say programming, but not so much. It's just really like the Excel world operations using technology, didn't really understand symbolic mathematics early on. Now they kind of do, and it's still like it still requires certain software like LaTeX, but it's not something that is very commonplace to find on a keyboard for like a traditional multiplication symbol. So it needed something else. So that something else ended up being parentheses and ended up being the asterisk. All right, with the dot being the one that was the chosen form of notation when it came to algebra. And same idea, it developed that the parentheses was also pretty convenient when it came to algebra, but the asterisk is mostly for technological purposes. And in fact, you'll even see when you work with certain calculators, you'll see the asterisk being employed rather than the like the dot. All right, and that dot thing, it catches students off guard when they first see it. They're like, "What is this weird notation? Is this like an alien language?" But in reality, it's actually pretty simple. It's just they got so used to the X that they fight, scratching and clawing to use the X still. Some of them are very, very embracing of change because they like the maturity that comes along with it. They say, "Oh, the dot, that's the grown-up version of multiplication. Oh, sign me up. I'm a big boy now." But then there's some that's like, "No, why are we changing? I fear change. I like the old way." So there's challenges and pitfalls either way. Right. That's a little bit of a background on that. Units. A sum has the same units as its terms. Very important. Multiplication, the units change, right? Depending on the situation, right? So I'll show you here really quickly. 5 yardsticks are placed end to end. For multiplication, sometimes it does have the same units as the original problem, if you will, but very often it doesn't, and I'll show you the circumstances in which it does or doesn't. Right, so 5 yardsticks are placed end to end. So let me make my yardsticks. Here's one of them. Two of them. 3 of them. 4 of them. 5. All right, end to end, each one valued at 3 feet. All right, so if you know each of them is 3 feet, then it becomes that multiple addition, or repeated addition, depending on how you like to say it. All right, so we're adding, and so on. And in the end, we get 15 feet. All right. Now, if we're using multiplication in its definition as multiple additions or repeated additions, what we're saying is that we have 5 3s. And those 3s themselves represent 3 feet. All right, so we have 5 of those 3, of those 3-foot measures. So the result is going to be 5 times 3, but we're still going to hang on to the feet. All right, because all we're doing is we're consolidating more and more feet together. And that's because we have, again, that idea of multiplier and multiplicand. but I'll focus on the multiplier part, right? So this is, when we talk about a scale of, geez, when we talk about a multiplier, we're talking about a scalar multiple. All right, what that does is it scales up or dilates your quantity. All right, so if I tell you that I'm 6 feet tall and I doubled my height, which is not likely, then it's pretty easy to say that I'm going to then be 12 feet tall, right? Because I scaled up my height, right? But I didn't change my units. My units are still feet, right? If I have, I don't know, an ounce, an ounce of something. Let's say just an ounce of some sort of liquid. I just drew a blank there for a second. It really doesn't matter. But if I tell you that I'm going to have then 5 more containers with an ounce of that same liquid, then you would say, okay, well, in total, I'll have 5 ounces of whatever that liquid is. All right, I'm scaling up the amount of liquid that I have. All right, it's when you include another dimension, that's when the units change. All right, so, and that's kind of where we're going to be in a few minutes. Right? So, fill in the blanks, another exploration, 3 days a week. Heidi walks 1 3/4 mile, or 1 3/4 miles. How many miles does she walk every day? All right, so 3 days a week. I'm sorry, how many miles does she walk every week? Her multiplier is 3. Right, she's doing it for 3 days a week. The single unit of measure is the 1 3/4 miles. So we have our repeated addition or multiple additions, 1 3/4 added to itself 3 times. Now you can do that, like I said before, where you do it, grab a calculator or whatever, or you could say, I got the 1, another 1, and another 1. 1 plus 1 plus 1 is equal to 3. And then I have the 3/4, 3/4, 3/4. Now here, I mean, you can count in 0.75s, but you could also just add across the top because you're looking at common denominators. So this would be 9/4, and then we can convert that over to a mixed number. It's 2 1/4. Put that together with the 3, and you get the 5 1/4. Right. So that's a little bit of a different way of operating on it, but it's still using addition as a shortcut to multiplication, right? Because otherwise, if you wanted to multiply, you would have to convert these over to improper fractions and then multiply across the tops and across the bottoms and simplify. Doable, but more convenient this way, right? Very, very important. Just make a note of it here. 1 3/4, and people very often lose sight of this. 1 3/4 is the same as 1 plus 3/4. That's why we're allowed to break up the 1 3/4 into separate values to be added. The 1's added together and the 3/4 added together. That's our license to do that because 1 3/4 already in and of itself is a sum. Right. So Sarah has 2 classes of 20 students. So 2 is the multiplier. The multiplicand is 20. So I would take my multiplicand and add it to itself an equivalent number of times as whatever the multiplier is. There's 2 of them. So I would have 2 20s being added. So we'd have 40 students. All right. Again, the idea, using addition as a shortcut to multiplication. It's very weird to think about it that way, but when you're doing computations by hand, when people are starting to develop the understanding behind arithmetic, it has to do with, I'm not going to pick up a calculator. I'm going to do it by hand. What's the easiest way to do it by hand? I could say 300 times 17. I give me a piece of paper, I'll figure it out. Actually, I mean, those are pretty nice numbers, so it's not that bad. But maybe there's an addition way of unlocking that. If I'm saying 300 times 17, I'm saying 317 times. Worst case scenario, you're counting by three. And going back to those fingers I was talking about before. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. So I'm already up to 10 of those threes. I need to have 17 of them in total. So 33, 36, 39, 42, 45, I'm up to 15, 48, and then finally 51. So 3 times 17 is the 51. They're counting by threes. Skip counting if you want. So I'm up to 51. Tack on a couple of zeros, and yet when you have it, right? So 5100. So I didn't get out a sheet of paper. I didn't write the multiplication algorithm 300 with a 1700. Oh, like, wait a minute, is this the one where I put the zero in there? I didn't do any of that. I just skip counted by threes, and I got the result of something that, it's not the hardest problem in the world, but it's not the easiest one either. So those kind of mental computations, they come from the idea of using addition as a shortcut to multiplication, right? Peter buys 3 half-gallon bottles of milk. So 3 is my multiplier. Each one of them is worth half a gallon. How many gallons of milk has he bought? Right? So the 1/2 is happening 3 times. We're using addition. We're looking at 1.5 gallons. What's 3 times 1/2? 3 halves, 1.5. The question, this is one of those, and actually the previous example and this one, kind of that gray area. Which way is easier? 2 times 20? Yeah, 2 times 20 is easier than 20 plus 20. I mean, not conceptually, but in terms of actually, what you would write down. This one, if you know enough to multiply, you're fine, but you're using the addition again as a shortcut. Now, the second part here, find the area, right? It's a centimeter grid, right? So each box is worth 1 square centimeter. So when I say a centimeter grid, each box is 1 square centimeter. All right. So this is kind of a different story here, because when you get into area, first we want to tackle the concept of that 1 square centimeter. Where on earth did that come from? And then from there, we want to find out, what the shaded area or shaded region would be, right? So I'm going to just focus on one of these rectangles. It doesn't, or squares. It really doesn't matter which one. I just don't want to accidentally shade something that isn't already shaded. So I'll take this one. All right, so highlighted in purple. I'll make it a little darker. All right. So the dimensions here are 1 centimeter by 1 centimeter. 1 centimeter by 1 centimeter. The area, 1 centimeter, base times height. 1 centimeter times 1 centimeter. Probably make that a little bit bigger. So 1 centimeter by 1 centimeter. All right, we know 1 times 1 is 1. But then the big question is, what's cm times cm? You know, if I told you numerically, 2 times 2, you'd say 4, but you could also say 2 to the power of 2, 2 squared. Right? So when you multiply cm by cm, we're actually getting cm as a multiplier of cm, the multiplicand. So that product is cm raised to the first power, to the second power, right? So I have 1 centimeter squared as being the area, right? So the cm's come together to give me a cm squared. And that's the progression, right? So I got one of them. Now I need all of them. Looks like I have 1, 2, 3, 4, 5 of those boxes. All right, so I have 5 shaded boxes. Each with area equal to 1, let's also say area of 1 square centimeter. So that's the same as saying we got the repeated addition, multiple additions, 1 centimeter squared plus 1 centimeter squared plus 1 centimeter squared, 1 centimeter squared. I'll throw the other one over here, centimeter squared. In total, that would give us 5 centimeters squared, or 5 square centimeters if you like. All right. Now that is the same as saying 5 multiplied by 1 centimeter squared. All right. So this is the scale factor, scalar multiple. When you have a scalar multiple or a scale factor, it's unitless. They're unitless. Unitless. I don't even know. It doesn't have any units. When it doesn't have any units, we're not concerned with that changing whatever the units were for the other part of it. All right. So our multiplier in this context is unitless. Our multiplicand has the units of centimeter squared. So our final answer would have the units of centimeter squared. All right. So in part B, it's kind of a weird question. What is the shape of the standard unit for measuring area? The shape, I really mean shape, it's going to be a square. Right? It's literally and geometrically a square. So it's kind of strange to think about it, but when you find the area within a circle, for example, what you're doing is you're finding it in square units, because whether it makes sense or not, a square, a circle can be kind of decomposed into the sum of different squares. I'll show you really quickly. It's not going to look pretty, but I want to kind of prove that to you. So you have a circle. That's not a circle, more of an ellipse. That's more of a circle. So what you can do is you can just break this up horizontally, with horizontal slices. Little ugly, but Well, it's all right. Trying to create some consistent spacing here. All right, and so we could figure out pretty much everything that is a square, the area of each one of these squares. Now there's a lot of them, so what I'll do is I'll just shade the ones that we wouldn't be able to figure out, because these little triangular regions we wouldn't be able to figure out. Just going to kind of work my way around. But we can get a fair few of them. Actually, all of this stuff would be out. So anything that doesn't create a square, we wouldn't be able to get. And so you'd say, well, how can we use square units to represent this? My answer to that would be, well, if we move the line segments closer to one another, we'll be able to get more squares into this circle. All right. So as it stands right now, I get everything but the green, which is, you know, it's not entirely a circle, but it's a pretty good approximation of it. What I'll do is I'll show you, instead of making more lines inside the circle, I'll put less in there to show you a less accurate case. All right, so here, I would not be able to find the area for any of these guys because they're not squares, or any of these guys, or any of those guys. So all of that stuff would be out. I wouldn't be able to factor any of that into the computation of the area of the circle. But if I move the line segments closer to one another, you can see that I'm covering more of the circle. If I were able to move them even closer, then I would have even more of the circle, right? So when we're talking about the area, even for things that aren't necessarily rectangular, you can still get across the same idea using rectangular measurements. It's just not always going to feel right, but that's okay. All right. So yeah, it's still, the standard unit is still going to be a square. Right? And there are some animations that show you how, as you increase the number of vertical and horizontal lines, you get closer and closer to a true representation of the area within a circle, and it's pretty cool. I'll see if I can put one together for you all, or at least find one. No sense in reinventing the wheel. All right, number 4, find the area of the shaded shape on the centimeter grid to the right. Okay, so it's the same idea. We know that each one of these figures is valued at 1 centimeter squared. So if we know what one single unit is, and we know how many units there are, then we got what we need. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're talking about 8 multiplied by 1, 2, 3. right? So these are, we're actually creating multipliers to generate a multiplier, which is kind of weird, but that's how it's going. Right, so that gives you a total of 24. Those are the boxes. Each one valued at one square centimeter. So 24 of the 1 square centimeter boxes is going to give us 24 times 1 square centimeter, which is going to be 24 square centimeters. You see here, it had that extra layer of the product of 8 and 3, right? Because when you think about it, it's like, okay, well, why did we know to multiply that? It's still following the same kind of relationship, the same rationale. It's kind of hidden in plain sight. So the 8 represents the number of columns. 3 represents the number per column. Right? We could say the number of rows in the shaded area, but really the idea of number of columns, that gives me the multiplier. The number per column, that gives me the individual value of a column, right? So that's the multiplicand. Finding the product of that gives us the number of boxes, because I'm saying 8 columns with 3 boxes per column gives us a total of 24 boxes. And since we know each box is valued at 1 square centimeter, that gives us 24 of those square centimeters. Right? So then looking at number 2, suppose each of those cubes on the right is 1 by 1 by 1. What's the total volume of this set of cubes? Let's focus on just 1 cube right now. Because again, that seems to be the moral of the story at this point, right? Looking at just a singular before we go too crazy looking for anything more complicated than that. All right. So we have 3 dimensions that make up a cube. You have the length, the width, and the depth, or the length, the width, and the height. You can say it a bunch of different ways. All right. So let me get rid of this one. So we have length, we got width, and we got height. All right. Now, in each case, it's 1 centimeter. All right. Now, we knew, and it's really kind of a formula, but more so it's like intuition. We knew area was base times height, so 1 centimeter by 1 centimeter, right? But what I want to do here is kind of illustrate for you the fact that a square, a cube is really just a square with depth. That's not a square. That's not a square. Still not a square. Definitely not a square. Square. All right. So if we know that this square has a base of 1 centimeter and a height of 1 centimeter, and its area is 1 square centimeter. All right. Now, if I tell you that this depth that I'm creating here this depth is also valued at one centimeter. It kind of begs the question of, right, how does that factor in? Well, let me just move this out of the way real quick. It still has to do with that whole multiplier multiplicand concept. All right. If I know that the area of that face is equal to 1 square centimeter, all right, what I'm really saying is, just kind of go back to the templated concept. You could even kind of flip back and just look at the rule here. The product M by B, total number of objects in disjoint sets, blah, blah, blah. And M is the multiplier, B is the multiplicand, that's fine. But it's B happening M times, all right? So number of sets, size of the set. We can look at this as the number of sets. We can look at this as the size of the set. Air quotes around it, but that's essentially what it's going to end up being. So it's like saying, and this is almost like a simplistic explanation. It's like saying I have an area of 1 square centimeter, and now I want to kind of project that outward. I want to say that I'm going to have 2 of those, or 3 of those, or 4 of those. That would be just a simple sum. But if I'm incorporating another dimension, what I'm now saying is that for every one of those 1 centimeters in 1 centimeter in depth, which is kind of a weird thing to say, for each part of that 1 centimeter in depth, we have an area of 1 square centimeter. All right, so we kind of look at it like little cross sections of square. So I'll just kind of try to accentuate it here. So everywhere along the way here, if we were to kind of cut this cube along those lines I just drew, you'd have a face. You cut it's like a stick of butter. Take a stick of butter, right? Let's assume that it's actually starting off being a cube shape, so it wasn't a full stick to begin with. And then you slice it vertically right down the middle. You're going to have that face when you separate the butter. The face is going to have the same area as the original stick. And if you cut it again and again and again and again and again, each face is going to have the same area. So really, it's just a matter of saying, okay, well, what's my length? Because if it's 2 centimeters or 3 centimeters or 4 centimeters, that's going to impact the total volume. Right? So what we're saying is, for each part of this cube's depth, it has a face area of 1 square centimeter, which gives us the 1 centimeter as the multiplier to the 1 square centimeter of multiplicand. All right. So that's the scalar multiplier. that's how we're scaling it up. Oh, I'm sorry, I pointed it to the wrong thing. The 1 is the scalar multiplier. Now the units play an important role because if I multiply centimeters by centimeters squared, I'm going to end up with centimeters cubed. So 1 times 1 is 1. Centimeters times centimeters squared is centimeters cubed. So that's kind of the origin story behind the volume, right? Because once you have a single standard unit for measuring volume, everything else is determined based off of that. So it becomes what we call a basis of volume, right? So this is the basis of volume. Just like 1 square centimeter was a basis of area. So this is basis of volume in centimeters. So assuming the linear units are centimeters. So you could already see that being a multiple choice question on a skills assessment, right? Which of the following is the basis of volume in centimeters? And it'll be like, okay, 1 centimeter squared, 1 centimeter cubed, 1 inch squared, or 1 square inch, 1 foot squared. I'll put an absurd one in there. I'll put like 1 mile per hour or something like that, just so you'd be like, well, that one can't make sense. But when we want the total volume, we have 3 cubes valued at 1 cubic centimeter each. So that's 3 of those 1 cubic centimeters, which is 3 times 1 cubic centimeter. Or you could do addition if you want, the multiple additions. And we get 3 cubic centimeters. All right. So the shape of a standard unit for measuring volume would be a cube. All right. Now those diagrams I drew for the circle with little squares inside of it that didn't really quite look like squares. I'm just going to ask you to imagine here because there's no way on earth I could actually draw this, me personally. I mean, I could find something online, a mock-up, a visual, but there's no way I can physically sketch it out. But imagine a sphere, and you're counting off the volume in that sphere with little cubes, right? So just think of it this way. Cube-shaped Legos. I know that's not really a thing, but where you can stack like little Lego pieces on top of one another and make it cube shape. If you were to try to build a sphere with those cube-shaped Lego pieces, you'd eventually do something that looks somewhat spherical, but if the pieces were smaller, the smaller they were, the more spherical it would look, the more smooth the outer surface would be. The larger those pieces were, the larger those bricks were, the more rigid and angular it would look like, right? So smaller is better in this context because it gets more of a fit, right? I kind of look at it like, if you wanted to fill a glass with ice cubes, you're going to have a lot of gaps with air, right? It's just the nature of things. Unless those ice cubes are really, really, really small. If you got the crushed ice, you can fill in all those little gaps. Not all of them, but a lot more than you would with regular, ordinary, standard cubes. Fill a glass with water, molecules are closer together, you're going to cover even more of the possible volume, right? It's the same idea here. The smaller the space between molecules, the more volume is covered, right? So in this, geometrically, that equates to smaller squares, smaller cubes. Cube on the left is measured in inches. Cube on the right is measured in centimeters. Which cube has more of its volume shaded? Justified by showing all computations. All right. Now, it's kind of a weird question. So the one thing that you got to kind of understand is that it's what you see is what you get. All right. So there's no more shaded cubes on the interior than there is on the exterior. So we're only counting exterior cubes. So we're not going to assume that it goes all the way through necessarily, at least for the one with the smaller cubes. So here I have 1, 2, 3, 4, 5. There are 6 sides to a cube. All right. So 6 sides to a cube. Let me get it over. And that's true in both cases. All right. So that's just a fact. All right. For the larger cube, the cube on the left. So on the left. We have a total of 5 shaded cubes per side. Each valued at 1 cubic inch. All right, so 5 shaded cubes per side, each valued at 1 cubic inch. Now for the other one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so on the right, we have 13 shaded cubes. Per side. Each valued at 1 square centimeter. I'm sorry, 1 cubic centimeter. I'll write it out like I did the other one. 1 cubic centimeter. All right, so we got some multiplication ahead of us, but nothing too crazy. All right, so first we'll start off with each side, each facet. So 5 times 1 cubic inch is going to be 5 cubic inches. (13) times 1 cubic centimeter is going to be 13 cubic centimeters. Now there's 6 sides. All right. So each side has a total amount of shaded in terms of the cubes. We're assuming the cube is shaded throughout. 5 cubic inches worth of shading, and also 13 cubic inches worth of shading. Also, now that I think about it, this might be a little too complicated just in general, because the shading for one side would also account for shading on the other. So let's just focus on just one side of the cube, right? More of its which cube? I don't really know how to reword it. It's just to say, let's just focus on just the first row, because otherwise we get into that overlap issue that becomes a problem. I mean, it's kind of a fun problem, I guess, but it's not really what the point of this lesson was. So we're only focusing on these guys. All right, so I'll show you what I mean. I'm kind of talking about doing this. It's not really a cube anymore, sort of like a prism. All right, and so same idea for the other one. It was originally supposed to be a trick question, but not too tricky. I'll show you what I mean by that in a minute. So none of this. Yeah, so something like that is what I was going for. The figure which one has more of its volume shaded, right? So that's kind of what I was going for. Anyway, so we don't need the 6 sides to a cube anymore. So these measures are actually correct now, or they were always correct, but just it would have been more complicated when it came to the entire cube rather than just one face. So try to make it a little simpler. So anyway, the reason why this is kind of a trick question, it says which one has more of its volume shaded? Like, well, it's really calling for a ratio here, right? So in this case, since they're all equally measured, we're looking at 1, 2, 3, 4, 5, so 9 equivalent volume cubes. So 5/9 of this is shaded. So 5/9 is shaded. For the other one, it was 13. I remember that. But as far as the denominator is concerned, 1, 2, 3, 4, 5, 13/25 shaded. All right. So which one has more of its volume shaded? It seems to be the case where, like we're just relating 2 fractions to one another. But if we wanted to know what proportion of the volume is shaded, then that's a little bit of a different story, right? And that's because there's 9 cubic inches to work with. All right, so 9 cubic inches in total. And for the other one, same idea. Again, a total, there's 25 of those cubic centimeters. Ultimately, this ends up being kind of a justification more than anything else that the units are irrelevant when it comes to the proportion of a whole, right? So we'd still need to know which one is a larger value, 5/9 or 13/25, but that's different conversation for a different day, really, right? So we could get a common denominator and compare them, but like I said, different story for a different day. All right. So what I'm going to do now is I'm going to stop the recording and